Well, first of all, I'd like to thank the organizers for inviting me to give this talk. I am very glad for having this opportunity, and what I'm going to show you are the results of my recent work. It consists of a mathematical simplification to the dynamical equations of the model when a gradient bumblebee field at its vacuum expectation value is considered, and also explicitly reviews how such kind of bumblebee field modifies spacetime. As a consequence, new solutions to the model can be found very easily, and some examples are given to show this. The bumblebee gravity model we are going to consider is given by this well-known and long-studied action. We will take the bumblebee one-form field as a dynamical variable, so one must bear in mind there is a contraction with the metric to form these contravariant forms of it. This B mu is the so-called bumblebee field strength and can be written equivalently this way. V is the potential of the bumblebee field, whose minimum is 0 and occurs when its argument vanishes, and its argument is written in terms of this lowercase b, which is a real constant. And you are also considering two sign possibilities in this argument. Ln is the Lagrangian density of any other field that may be considered. By performing the variational procedure, we are led to two equations, one associated with the variations of the metric and another one associated with the variations of the bumblebee field, both giving their dynamics. The energy momentum tensor is decomposed in terms of the contributions from the bumblebee field and from Lm. The contributions from the bumblebee field are given by this expression. The first dynamical equation can be equivalently rewritten in this form given the Ricci tensor in terms of the energy momentum tensor, where T is the trace of the energy momentum tensor. And this will be the expression we are going to consider in this work. So these are the dynamical equations that describe our bumblebee model, and there's nothing new to anyone, right? Now, if we are interested in the consequences of this bumblebee field, either to validate the model or to constrain its parameters, we must know how to describe the different situations we may consider in this scenario. So, we must know the solutions to these dynamical equations for those situations. But what are the solutions to such a complicated set of differential equations? This is what my talk is all about. And what I'm going to show you is how solutions can be easily found in a particular case of this bumblebee gravity scenario. In this particular case, we will not consider any other source field besides the bumblebee. We do not intend to solve for the interior of a star for the moment, right? Nor even to consider the presence of some electromagnetic field, and the cosmological scenario is not our point now. For the sake of simplicity, we will be seeking solutions to the vacuum, so the energy momentum tensor will have only the contributions from the bumblebee field. Also, we will consider that the bumblebee field is at the minimum of its potential, or, in other words, that it is at the so-called vacuum expectation value. This is a somewhat usual assumption for the bumblebee field, and it eliminates these terms from the dynamical equations. Now, as a second consideration about the bumblebee field, let's take it to be given by the gradient of a scalar function, which I'm calling lambda here. So, as a consequence, the bumblebee field strength vanishes, which also leads to this equality that the bumblebee field satisfies. The vanishing of the bumblebee field strength eliminates these terms from the dynamical equations, and the second dynamical equation now states that the contraction of the bumblebee field with the Ricci tensor is null. This in turn eliminates these other terms from the energy momentum tensor, which now simplifies to this expression. With this result, the equation for the Ricci tensor simplifies to this expression, and we can simplify it even further, making use of this property that the bumblebee field satisfies for being a gradient of a scalar function. So these are the dynamical equations we need to solve in this particular case. But now, since we have an expression for the Ricci tensor in terms of the bumblebee field, what does the second dynamical equation tell us about this right-hand side? Let's contract it with the bumblebee field and see what it gives us. Passing b mu into the covariant derivative and discarding its contribution, we arrive at this result. And that same property that the bumblebee field satisfies for being a gradient of a scalar function now gives us this expression for the contraction with the bumblebee field. But it is a well-known result that this right-hand side vanishes when the vector has a constant modulus. So this will eliminate these two terms on the right-hand side of this contraction of the bumblebee field with the Ricci tensor. So the second dynamical equation is actually already satisfied by the first one, which is then the only dynamical equation we need to solve in this particular case. In summary, our bumblebee gravity model in vacuum is described by a single dynamical equation when the bumblebee field is at its vacuum expectation value and is also a gradient. The property of being a gradient in turn can be equivalently rewritten in terms of the partial derivatives. Even though the dynamical equation is already very simple, we can simplify it even further, making use of this G mu tilde defined this way, whose inverse is given by this other definition. And one should notice that it is actually a new definition, since you cannot pass from one to the other making use of the metric. But they must be defined that way so that one is the inverse of the other. With these definitions, we can split the metric in terms of this G mu tilde and a contribution from the bumblebee field. And the same goes with the metric inverse naturally. Now we have this metric splitting, we may rewrite the Ricci tensor in terms of the G mu tilde and these contributions from the bumblebee field. For that purpose, first we must substitute these expressions in the affine connection, which is given by the Christoffel symbol. A straightforward calculation leads us to this result, in which the first term on the right-hand side is precisely what the connection would be if the metric was replaced by this G mu tilde. So we may call it a connection tilde. Now we have a corresponding splitting of the affine connection, which is now written in terms of a connection tilde, which is the Christoffel symbol constructed with the G mu tilde instead of the metric, plus a contribution from the bumblebee field. If we now replace this expression in the definition of the Ricci tensor, another straightforward calculation leads us to this result, in which, once again, we may identify an expression which corresponds to the Ricci tensor written in terms of the connection tilde instead of the connection. So again, we have another splitting in which the Ricci tensor is written in terms of a corresponding Ricci tensor written only in terms of the G mu tilde plus a contribution from the bumblebee field. Placing this result in the dynamical equation, we see that the contributions from the bumblebee field cancel out. And the single dynamical equation becomes even simpler. It now states that the G mu tilde satisfies the Einstein's equation in vacuum, which happens to be the same equation for this bumblebee gravity scenario in vacuum when there is no bumblebee field, when it is absent. For that reason, it will be called the background metric from now on, since this is just what it actually is. It describes how spacetime would be in the absence of the bumblebee field. So, this metric splitting is giving precisely how a gradient bumblebee field at its vacuum expectation value modifies a vacuum background, and these are the changes it brings to spacetime. Furthermore, we now have a very simple way to get solutions to the model. It basically consists of having a background metric at hand, a gradient bumblebee field at its vacuum expectation value, then we join them together according to this metric splitting to get the solution. However, how can we impose the condition on the bumblebee field modulus if that depends on the metric solution we are still about to obtain? No big deal. It's just a matter of writing the metric in terms of its corresponding splitting, do some algebra, then we arrive at an expression that relates the bumblebee field modulus according to the background metric with its modulus according to the spacetime metric solution. Since it is a constant, the background modulus, let's call it that way, will also be a constant, namely this one. Now we have a systematic approach for obtaining solutions to this bumblebee gravity scenario. Having a background metric that solves Einstein's equation in vacuum, we take a gradient bumblebee field with a constant modulus according to that same background metric. Then the metric solution is given by this expression. So the task of obtaining solutions to the model is basically as difficult as finding vacuum solutions to the Einstein's equation. It only requires the extra work of obtaining a gradient field with a constant modulus. If a vacuum solution to Einstein's equations is already at hand, the task becomes substantially easier. All you have to do is finding a bumblebee field with these properties. In any case, it is remarkable how it is just a matter of having this for the solution to be ready without any additional work. All these results, along with the remaining of my talk, can be found at this paper I published last year. This particular case is summarized by these expressions, and now we know how the bumblebee field modifies a background spacetime. In this sense, let's see how some already known vacuum solutions are modified by its presence. Let's start by taking Schwarzschild spacetime as a background. Everyone knows it is a vacuum solution, and as a first proposal for the bumblebee field, let's consider it has only the radial component and that it only depends on r. It is clearly a gradient, and for it to have a constant modulus according to this background metric, its radial component must be given by this expression. Placing this background metric together with this bumblebee field in the metric solution provides this result that has already been published previously by myself and colleagues in this paper, but now obtained in a much simpler way. However, this same approach makes it just as easy to consider an even more general possibility for that field. So let's consider it to be given by this expression now, which has a constant arbitrary time component. It satisfies the required assumptions, and the corresponding metric solution will now present cross terms due to this contribution from the bumblebee field, which will be non-zero for indices 0 and 1. Nevertheless, in this case, it is just a matter of making a convenient coordinate transformation to make the metric diagonal. As a result, the solution is basically the same as the previous one, the only difference being in this constant L', which presents this arbitrary B0 component, whereas it was L before and with no arbitrariness at all. In that paper where the previous solution was published, this limit was set for this constant. Well, actually it was for L, but it translates to L' in this case, right? But due to the presence of the arbitrary B0, it is now impossible to establish any limit to the parameters of the theory combined in L, which is xi times b squared. Well, now, as a second and last example, let's consider the changes a gradient bumblebee field at its vacuum expectation value may bring to Kerr spacetime, which describes a rotating black hole. Its spacetime interval is given by this expression, which can be regarded as a background spacetime interval, from where we can extract the background metric. It is a vacuum solution, and as a rather general proposal for the bumblebee field, let's consider it to be given by this expression, in which B0 and B3 are arbitrary constant components. It is clearly a gradient, and the other components must be given by these expressions in order to satisfy the constant modulus condition, where C is an arbitrary constant. Placing this background metric and bumblebee field in the metric solution, one can imagine how complicated it will become. There will be no single metric component that is null because of this contribution from the bumblebee field and the fact that all its components are non-zero. This is a clear example of how powerful this approach is, as I'm pretty safe to say no one would ever find such a complicated solution otherwise. In fact, even checking that this solution actually solves the original dynamical equation written in terms of the metric and bumblebee field would be a difficult task already. Just imagine calculating the connection and reach tensor from such a metric with all its components non-zero. This is something that basically only a computer can do if you want to be confident of the result. It is actually kind of funny how it is easier to check this approach is right in a general case than it is to check the specific solutions that it allows to be found. Anyway, the presence of this arbitrary B3 makes components B2 ill-defined. Therefore, regardless of it being a coordinate issue, let's set it to 0. By doing this, we eliminate these terms. Also, for simplicity's sake and seeking the least modifications the bumblebee field brings to space-time, let's set its time component to 0. As a consequence, these other terms are eliminated. Now, to simplify the bumblebee field the most, let's set the arbitrary constant c as a squared. The bumblebee field is now just as simple as it can be, and the resulting metric solution provides this space-time interval. The changes on cache spacetime are highlighted in orange, and as far as I'm concerned, this is the first rotating black hole solution to this bumblebee gravity scenario, which is valid for any rotation, either slow or fast. And it is remarkable how easily it was obtained by means of this approach. Because of the specific form of the bumblebee field, it introduces a new cross term in the spacetime interval associated with coordinates r and theta, which cannot be removed by a coordinate transformation. However, it must be so if it is supposed to be a gradient with a constant modulus. Therefore, if someone wants to find a Kerr-like solution without this cross term, a different bumblebee field becomes necessary, and this approach would not apply, taking the treatment of the dynamical equations back to square one. Despite this cross term, the solution still represents a rotating black hole, and its distinguished surfaces are still given by the same expressions as the Kerr solution, r plus minus infinity being its infinite redshift surfaces, and r plus minus infinity being its horizons. In conclusion, a great simplifying approach was established to this bumblebee gravity scenario, where a complicated set of dynamical equations were reduced to Einstein's equation of general relativity in vacuum when the bumblebee field is a gradient and at its vacuum expectation value. As a consequence, new solutions to the model can now be very easily obtained, making it possible to analytically describe spacetime geometries of great interest. As the approach is valid to vacuum, it applies to a wide range of possibilities. The influence of the bumblebee field on the spacetime description is explicitly provided in the metric solution as a term added to the background metric. As a result, one can now easily determine and constrain its specific effects on any astronomical phenomena. On the other hand, this consists of a particular case of the whole model. Even though the solutions provided consist of solutions to the whole model as well, the consequences of them concern only a particular type of bumblebee field. Besides, we could see there is some arbitrariness in the solutions that make it impossible to establish any constraint on the theory's parameters. Even when the arbitrariness is removed, we can only constrain L, leaving C and B still undetermined individually. I haven't shown it, but one can see that the bumblebee field doesn't need to have a specific modulus. It can have any constant modulus, as it will be the normalized version of it that will enter the metric solution. Normalized according to the background metric, so it will not present any of those parameters at all. Any intention of getting anything different from these conclusions must necessarily involve another type of bumblebee field. And in this sense, I believe some important aspects of this bumblebee gravity scenario are now well addressed. I acknowledge the financial support of the Brazilian agency FAPEMA. Thanks for the attention.